Hello, everybody. In the portion of the lecture that I wanted to highlight here at the tail end of section 9.3, we are going to focus on this sort of newer kind of series that's known as a P series. A P series, it's going to be very, very easy to recognize typically. It has its, very characteristic form that's just pretty much difficult to not pick up on. And what you want to look for is a rational function, that would be a fraction, that has the form 1 over n to the p. Now, what's going to be important for you all to realize is that this p, this exponent that you see within this p series, is going to be a constant. It doesn't change. It's the base of that exponent that we call n that you see changes because of the boundaries of your summation. All right, now what p is equal to has a big bearing on what the behavior of the series is going to be. Now, aside from the p series, we have this other type of series that's known as the harmonic series. Our harmonic series is a p series, but it specifically will have a value of p that's equal to 1. And in class, we talked just briefly about the connection between the harmonic series and music theory, and how various characteristics of musical instruments, with whether they're stringed instruments or brass instruments or woodwind instruments, will demonstrate harmonic tones between two notes if they maintain a relationship based on the 1 over n. Now, these two series don't sort of do the same thing all the time. They don't always diverge, they don't always converge. It is very dependent upon what the value of p is. And as you can see here in the blue box, it seems pretty clear what's going on with each of these. If you've got a p series and the p value is larger than 1, strictly larger than 1, you will have a series that will converge. Now, the thinking behind this may not be too difficult to see, in that if you have a power larger than 1, it seems like you're going to experience a tremendous amount of growth within the denominator, especially as n counts from 1 to infinity. And as the denominator gets pretty large, the number itself, the term, is going to become pretty small, and so you're adding infinitesimally small numbers by the time you get out to the very end of this series, and you can construe that, yeah, that's going to approach a finite value, thus it makes the series converge. On the other hand, if you are looking at a p-value that is between 0 and 1, and it's okay if we want to call that fractional, that's typically the way that it would be presented. It could be a decimal. Say if p is 0.95, that would fit into this category, and you would have then a series that will diverge. Now, just briefly here, we could take a look at example 2. We're just determining whether this series will converge or diverge. It is a p series, but it doesn't have the specific p series form like we see up here in the box, where we see the summation, and we could instantly recognize what the value of p is going to be. But don't let something like that bother you, because all it's going to do is take just a little bit of thinking, and we could take this particular written out term by term series and we could write a summation expression for it. So let's get to that. Obviously, things are going to start off like this. That's seemingly the easy part. And then you look at each term and you kind of ask yourself, what do we see that's in common from one term to the next? Well, I think one thing that's pretty obvious is that each term is a fraction. Now, of course, you might want to argue that for this first term, but 1 can be written as a fraction, 1 over 1, or perhaps in this case 1 over the cubed root of 1. So that means that the numerator is always 1. Well, looking at the denominator, you'll see that, well, yeah, we do seem to go from a base value from 1 to 4 to 9 to 16, etc., which means we definitely are looking at a squared relationship. Our n value is being squared, but at the same time, we're taking a cube root. Now think about that. when you're squaring a number and cube rooting it at the same time, isn't that the same as taking that number to the 2/3 power? Now, if that bothers you, there's nothing wrong with temporarily thinking of that denominator as being the cube root of an n that would thus be squared. But you'll see that there is a direct connection, equivalence, in fact, between those two terms. So hopefully it becomes very easy to see that, yes, p is 2/3. Okay, we go and we'll see which category does that seem to fit in. Well, that would be category number 2. We diverge if p is between 0 and 1, and thus we have our divergent series. Recognizing the behavior of a p-series should be one of the easier things that you guys do in Chapter 9.